In general, populations are made up of different kinds of individuals. There are males and females. There are small individuals and large individuals. And there are the young and the old. When the differences among individuals influence demographic processes like survival and reproduction, models of population growth must be adjusted if useful predictions are to be obtained. In this video, we'll focus on age-related differences among members of a population. We'll leverage what we know about vectors and vector-valued functions to model population growth in a way that accounts for age-related impacts on demographic processes. Let's jump right into an example. Consider a population made up of two kinds of individuals, juveniles and adults. Let the vector x of t give the age distribution in the population at the beginning of year t. Specifically, let the first element of this vector give the number of juveniles in the population at the beginning of year t, and let the second element give the number of adults in the population at the beginning of year t. I'll note that conventionally, models track only female juveniles and only female adults. That said, we don't have to emphasize this convention in order to understand the technical modeling details at play. Consequently, I'll just refer to juveniles and adults going forward. Speaking of going forward, let's make some assumptions. Let's assume that exactly 30% of the juveniles encountered at the beginning of year t survive to the beginning of year t plus 1, and further that they're counted as adults at that time. Let's also assume that exactly 80% of adults encountered at the beginning of year t survive to the beginning of year t plus 1. Finally, we'll say that every adult we encountered at the beginning of year t produced two offspring who are themselves counted as juveniles at the beginning of year t plus 1. Let's now turn the assumptions reflected in this network diagram into a mathematical model. To do this, we'll stick with our tried and true recursive approach. Based on the assumptions we made, we can express the number of juveniles at the beginning of year t plus 1 as 2 times the number of adults counted at the beginning of the previous year. We can also determine the number of adults at the beginning of year t plus 1 by recognizing that they're made up of the juveniles and adults respectively who survived from the beginning of year t. We should note that our recursive formula for the age distribution in the population can be expressed as a vector field. In fact, we can go a step further and write the vector field as follows. We can even write it in a rather unfamiliar way like this. This 2x2 array of numbers is called a matrix. As you can see, we've written it beside the vector x with x on its right. This signifies matrix vector multiplication. In general, when we multiply a matrix A by a vector x, written as AX, the result is a new column vector whose number of elements matches the number of rows found in the matrix. Importantly, we get the ith element of the new column vector by dotting x with the ith row of A, thought of as a row vector. Let's now get some practice with matrix vector multiplication by using our recursive model to answer the following question. If there are initially 10 juveniles and 5 adults in the population, then how many of each will there be after 2 years? We first determine the composition of the population after 1 year by applying the matrix from our model to the initial age distribution stored in the vector 10, 5. This matrix vector multiplication gives us the new column vector 10, 7. We got 10 by dotting the vectors 0, 2 and 10, 5. And we got 7 by dotting the vectors 0.3, 0.8 with the vector 10, 5. After 1 year, then, there are 10 juveniles and 7 adults in our population. To see where the population is after 2 years, we again take our matrix, but this time we apply it to the distribution from the end of year 1, like this. Carrying out the matrix vector multiplication leads us to predict that the population consists of 14 juveniles and 5.6 adults after 2 years. If you're worried about what 5.6 adults looks like, just think of it as an average, along the same lines as what we mean when we say the average couple has 2.5 kids. We could have represented the age distribution after 2 years as the matrix A applied to the column vector A 10, 5. Equivalently, we might say the matrix A is applied twice on the left to the initial age distribution. Thinking in this way, we can see that a model for the relationship between the age distribution and time in years k could be expressed in a non-recursive way by applying the matrix on the left an appropriate number of times to some given initial distribution. Like I said, this is a non-recursive formulation of the model. But even in this non-recursive form, it's difficult to judge if population growth, like the kind we've observed in this example, will be sustained over the long term. This brings us to our next point. It turns out that we can make predictions about the long-term behavior of the population without resorting to tedious computation. In a way, you'll be more easily convinced of this point after you watch later videos. But I can still present some supporting evidence using the mathematics we've discussed so far. To see what I mean, let's take our recursive model and modify it like so. Notice I've subtracted x1 of t from both sides of the first equation, and I've subtracted x2 of t from both sides of the second. If delta x1 of t denotes the change in x1 that occurs during year t, then we see that this change is equal to 2x2 of t minus x1 of t. Similarly, if delta x2 of t denotes the change in x2 that occurs during year t, then we see it is equal to 0.3 x1 of t minus 0.2 x2 of t. By plotting this vector field, the one that corresponds to changes in the numbers of individuals in the population, we obtain a sense of what happens to the population itself in the long run. When we plot the vector field that describes these changes in the age distribution, this is what we get. You see that no matter where we start, the number of juveniles and the number of adults both grow without bound over time. You can also see that the relative numbers of each appears to stabilize over time in that the flow suggested by the plot leads us to travel eventually along a line like this. More about that in later videos. For now, let's recap. We first learned how to build a model for population growth when an individual's age has implications for demographic processes like survival and reproduction. We next saw that a linear vector-valued function can be represented using an object called a matrix. We also saw how to carry out matrix vector multiplication, A times X, to make predictions about future age distributions in a population. Finally, we got a glimpse into the long-term behavior of a model for growth of an age-structured population, but more details are needed, and indeed more details are coming. At this point, you should be able to do at least 3 things. You should be able to translate information about demographic processes, presented in words or as a network diagram, into a recursive model for population growth. You should also be able to make predictions about the distribution of individuals across age categories after a fixed period of time and in the long run. When it comes to predictions about the long run, though, for now, your statements will be more qualitative than quantitative. Lastly, on a technical note, you should also at this point be able to carry out matrix vector multiplication. Don't forget that success in math is rarely achieved by only watching video lessons. You're probably super tired of hearing me say that, but it's true. Read, think, and discuss. Maybe even play around with different versions of these age-structured models and see what you can and can't get them to do. If you do that, I think you'll see that time spent with math really adds up.